The conflict is not theory, it is 1 hectare. Raspberries grow below raised photovoltaic rows, while sheep settle in the shade between them. Same land, 2 demands. Vegetables can occupy the strips under panels, and cattle can graze where standard solar farms would fence off production. In the United States, the pressure is already measurable. Solar build-out could need more than 4 million hectares by 2050, and over 80% of that area may overlap farmland. That turns each site plan into a land use decision, not just an energy calculation. The technical shift is height, sensing, and control. Elevated panels leave working space below, sensors track field conditions, and automated control adjusts shading and output. Raspberries make the case concrete. Overheated fruit and sun scald can damage yield, so shade is a physical variable. This combined approach already has a technical name: agrivoltaics. After the raspberry rows, the technical name leads back to Germany. In 1981, Adolf Gutzberger and Armin Zastrow proposed 1 field with 2 outputs, 1 crop area, 1 power plant above it. Their idea became agrivoltaics, often shortened to APV in German research. The first frame is not a farm scene, but a scientific proposal. The question was land geometry. Can solar modules collect light while crops still receive enough radiation, air movement, and machine access? APV answers by placing food production and photovoltaic generation on the same parcel, not on separate sites. Rows of modules rise above the ground while plants continue below or between them. The second frame is the field itself. Leaves sit under raised panels crossed by alternating bands of light and shade. That pattern matters. It changes heat stress, evaporation, and photosynthesis hour by hour. The design does not remove farming from the site. It changes the overhead structure that farming must work under. Then the scale hits. The United States Department of Energy estimates solar projects could need more than 10 million hectares by 2050. That is roughly the area of Iceland. At the same time, the world loses nearly 24 billion tons of fertile soil each year, mainly through erosion and climate pressure. Land is no longer a background detail, it is the constraint. Fraunhofer later moved the concept from paper into field trials, including a pilot site at Hegelbach launched in 2016. Its institute estimate gives the third compared with separating solar arrays and fields. APV can raise land use efficiency by 60 to 70%. Next comes the layout problem behind that gap: 60 to 70%. That efficiency gap points back to layout, not theory. A conventional solar plant in the United States often needs about 4 to 5 hectares per megawatt, then closes the field with low-mounted rows. Fast expansion began in the early 2000s, when utility-scale solar became a major alternative to fossil fuel power. 1 gigawatt changes the scale. More than 4,000 hectares, about 40 square kilometers. In a wide aerial shot, the array becomes a dark grid across former farmland, with access roads, inverters, cable routes, and repeated steel supports cutting the parcel into fixed lanes. The detail is underneath. Panels sit close to the ground because shorter posts reduce steel use, foundation loads, and installation cost. Dark bands fall under the modules, the lower edge hangs near the soil, and dense rows leave only controlled strips for maintenance crews. That geometry saves money on land and hardware, but it removes normal farming access. Narrow row spacing can reduce site costs by packing more capacity into one parcel, yet tractors and trailed implements cannot turn, lift, or pass safely under the modules. The machine reaches the gap, it stops, so the land usually keeps only low-risk uses. Beekeeping can remain around the edges, and sheep can graze weeds under the panels. Cattle and horses create a different risk profile because large animals can strike supports, chew cables, or damage exposed infrastructure. The conflict is not abstract, it comes from height, row pitch, and clearance. If one plot must produce both kilowatt hours and crops, the next check moves under the array. Raise the supports, widen the rows, and control the moving shade. After the fight over each hectare, the test moves into the structure. The array rises 3 to 5 meters, while dry regions use vertical rows to preserve machinery access and reduce exposed soil loss. Conventional solar rows mainly chase electricity. This layout must preserve field operations. It is geometry under control. First, the panel face takes direct sunlight from above. Then the rear side collects light reflected by the ground, so soil color, crop cover, and surface moisture change the gain. Bifacial modules can add about 5 to 10% generation over conventional panels when reflected light is strong enough. Pale dry soil helps more than dark wet ground. The camera drops beneath the raised row. A tractor passes through the clearance, followed by a seeder or harvester using the same corridor. Shadow bands cut across the soil, and dry dust hangs near the tires. Above, the frame must carry electrical equipment without blocking field work. 3 to 5 meters is the working gap. In arid fields, vertical panels change the exposure pattern. They catch low morning and evening sun, while the gaps receive different light through the day. The rows also reduce wind speed near the ground, which can limit erosion and slow desertification on exposed land. The wind is quieter between the panels. Dust still moves, but less sharply. Control is the second half of the design. Weather sensors and automated controllers track soil moisture, temperature, sunlight intensity, and crop growth. Artificial intelligence can compare those readings with power output and crop stress signals, then select a new panel angle. Changing tilt also changes light between rows and module heating. A motor creaks, the shade shifts, and the actuator turns the panel. Panel geometry matters until a leaf hits the light saturation point, where extra light no longer feeds photosynthesis. Why can panel shade help yield? Past that point, surplus light becomes heat load, draining the crop's water budget. The contrast is technical. More light arrives, the leaf cannot use it. Heat stress raises evaporation and reduces growth efficiency. In some crops, overheated stomata close, carbon dioxide intake falls, and photosynthesis slows despite irradiance. In hot weather, crops can lose up to 95% of absorbed soil water just to cool tissue. Partial shade cuts leaf overheating, reduces water loss, and can improve water use efficiency. The crops named here are lettuce, spinach, tomatoes, and soft berries. The next check moves from leaf physiology to measured field plots. Fraunhofer compared adjacent parcels near Lake Constance from 2016 to 2018. Same crops, different overhead conditions. One plot sat under APV modules, while the neighboring field stayed conventional, so weather, soil, and farm management could be read against each other. The site opens in a low agricultural landscape near the lake. Beneath the modules, light turns soft and diffuse. The shaded soil looks darker, with more moisture held near the surface. On the open plot, direct radiation hits harder, and evaporation rises faster after rain. That contrast is the test. Then the chronology shifts. In 2016, cooler and wetter weather favored the open field, and yields beneath APV fell by about 25%. The panels reduced useful light more than they reduced heat stress. A clean warning. Agrivoltaics was not an automatic yield gain, but the next seasons changed the result. In 2017 and 2018, heat and drought pushed the conventional plots harder. Under the panels, lower direct radiation reduced leaf temperature and slowed water loss from the soil. The APV parcels then outperformed the open fields because microclimate mattered more than full sun. That is why field trials matter. They include season, rainfall, and site microclimate, not just a single plant response in isolation. The same hardware can penalize yield in a wet year, then protect it during heat and water deficit. The background number is already more than 1.1 degrees Celsius. After the field measurements, the question moved to a fixed address, Baberich, near the German border. On 4 hectares, Groenlevin and Baywa tied a raspberry farm to a 2-megawatt agrivoltaic plant with 3 hectares under modules. That output can cover hundreds of households, but the harder test stayed at crop level. Raspberries bruise under hail, lose canes in strong wind, and suffer when heat builds inside protective tunnels. The old layout was familiar, long plastic covers running over the berry rows for hundreds of meters. Wind rustled through the alleys and film snapped in gusts above the fruit. In Baberich, the plastic disappeared and a rigid roof of solar modules took its place. The sound changed. Hail and wind met a dull strike on hard glass instead of the loose clap of stretched film. The engineering problem then narrowed to light. The panels used an east-west orientation, which usually gives a flatter generation curve across the day than a south-facing peak, making the electricity easier to use on site. At the same time, that roof had to block wind without starving the raspberry leaves below. This was no model. Growers and energy planners studied the site because protection, yield, and power output now depended on one field design. Light became the constraint. The first conventional modules produced too much shade, so protection and power started to cut into photosynthesis. The team kept the farm layout, kept the solar roof, and changed the module itself. They abandoned continuous panels and moved to a design with wider gaps between the photovoltaic cells. On those same 3 hectares, the next test arrived with summer storms. Wind and hail tore plastic covers on control rows, while a rigid solar roof already stood above the fruit. The contrast was immediate. The old film snapped and cracked under hailstones. The modules produced lower, duller impacts. Then the rows were inspected. In the conventional plots, some control fields lost nearly their entire harvest after the coverings failed. Under the panels, the raspberries showed almost no meaningful weather damage. Quality did not fall. Yield did not fall. In several comparisons, berries under the array performed better than berries in open conventional rows. For a soft fruit selling around $6 to $12 per kilogram in Europe Europe and the United States, one strong weather episode can cost farmers hundreds of thousands of dollars. The second test was less visible but just as important. The air under the modules changed. Temperature readings beneath the agrivoltaic installation sat several degrees Celsius lower than nearby control areas. Pickers moved through cooler aisles, with less heat trapped around the fruit and leaf canopy. That cooler microclimate reduced stress on raspberry plants during dry spells. It also slowed water loss from soil and irrigation lines, so the same field needed less pumping. The thermal benefit also reached the modules above the crop. Raspberry leaves release moisture through evapotranspiration, and that moisture cools the air around the panel backs. Silicon photovoltaic modules lose part of their output when cells overheat, so cooler air can protect generation while the roof protects the crop. Two measurements now mattered together: berry condition after storms and cell temperature during hot days. Not presentation logic, field logic. The value came from avoided damage, preserved fruit, and lower water use. In dry periods, irrigation demand fell by up to 50%.
Once water demand moves toward half, the farm ledger changes. A 2-megawatt agrivoltaic site gives the grower a second cash line. Crop sales remain first. Power sales now sit beside them. That matters in a bad weather year. In the United States, more than 50% of family farms bring in less than $100,000 annually. Fuel, fertilizer, and long droughts squeeze that margin further. One storm can reduce the harvest, but the panels still generate electricity. The timing is not random. Solar output usually peaks during summer, when pumps, cooling units, sorting lines, and storage rooms draw heavily from the farm meter. Part of the electricity can stay on site before any export. The rest goes to the grid. Even a few megawatts can bring hundreds of thousands of dollars each year, depending on location and power price. Lower fossil fuel demand is the technical side effect. The surplus electricity sale remains with the farmer even when weather cuts the crop. With crop revenue already paired with power sales, the same rows acquire a third task. Sheep enter the array, and vegetation control becomes farm work rather than a maintenance contract. The shift starts with a practical problem. Grass grows between module rows, seed heads reach cable trays, and tractors struggle under the low panel edge. On hot days, the service corridor becomes a green tunnel, with inverter access, cable routes, and fire clearance all depending on grass height. Then the flock moves in. Hooves press through dry stems, tags ring softly, and sheep graze under the even shade of the modules. No mower deck, no herbicide pass. After grazing, the service lanes open again, and technicians can reach combiner boxes and inverters without pushing through weeds. That is why sheep grazing has become one of the fastest growing agrivoltaic models. Across the United States and Europe, solar farms already graze sheep directly beneath panels, and the American Solar Grazing Association reports tens of thousands of hectares using this approach in the United States. A large solar site can spend tens of thousands of dollars each year on vegetation management. Sheep remove much of that bill with almost no added site cost, while creating farm revenue through wool, milk, or meat. Cattle are taller and heavier, so they carry higher risk around frames, glass, and wiring. Sheep stay lower, move lighter, and fit the geometry of raised rows. Panel shade also reduces summer heat stress during grazing hours. By the end of the pass, the rows are quiet. Short grass, working panels, and a slower question ahead over permits, land status, and cost. After a farm has already produced both crops and kilowatt hours, the bottleneck moves from the field to the permit desk. The hard number arrives first. Agrivoltaic electricity often costs 10 to 20% more than power from a conventional solar farm. So the next question is not whether the rows can grow food, it is who can approve them. The first stop is local resistance. Residents sit through a hearing room where the air is still, the microphones click, and the drawings line the walls. Many communities do not want large energy projects beside homes. The same pressure seen around wind farms and biogas plants in several states. Agrivoltaics adds a sharper concern. An investor can present farming as the reason for a solar build-out, while the neighbors see a power project arriving under an agricultural label. Then the file enters regulation. One parcel now carries crops and electrical equipment, so its status becomes contested: agricultural land, energy infrastructure, or a hybrid category. Subsidies become unclear. Ownership becomes unclear. Maintenance responsibility becomes
becomes unclear. In Japan, officials began creating separate rules for solar sharing in 2013, which shows why dual land use needs its own legal track. Without that track, projects can wait years before approval. The final constraint is the structure itself. Higher support frames leave working room for crops, machinery, irrigation, and service crews, but they add steel, foundations, and engineering time. The layout must protect sunlight for plants while keeping module spacing, cable routes, inverters, and access paths serviceable. Push the design toward electricity and crop shade can rise too far. Push it toward farming and output falls. The site stays empty, the plan set stays open, and construction does not start until land status, ownership, subsidies, and maintenance are approved. After years of permits and raised frames, the logic tightens. One site can carry crops below and solar modules above. Food leaves the soil, current leaves the rack. The contrast is blunt. Land, fresh water, and grids tighten together. Agriculture takes about 70% of global freshwater withdrawals. The UN projects nearly 9.7 billion people by 2050, adding pressure on fields and power. Agrivoltaics returns because it links area, water, and connection in one layout. Under panels, the field looks less unusual. Scale becomes the constraint. After the field under panels, the scale changes hard. Over 2 decades, China moved toward nearly 30% of global industrial output. That scale changed the problem. One farm could test land sharing, but factories required national power. The first frame is industrial output rising across ports, steel plants, and assembly lines. Demand moves through transformers, rail yards, and furnaces. Coal fills the gap. At one point, it supplied up to 70% of China's electricity, while the country consumed more than half of the world's coal. The second frame is darker. Dense smog sits over a major city and the horizon turns gray. By 2010, China produced about 30% of global carbon dioxide emissions. Air quality became a domestic engineering problem, while climate targets became an external constraint. Beijing then changed the energy plan from scattered trials to large desert deployment. In 2020, China announced carbon neutrality by 2060. The same official framework fixed an emissions peak before 2030. This added a deadline, not just a target. The third frame cuts from gray air to a dry map of northern and western deserts. The National Energy Administration has named desert, Gobi, and barren land bases as core renewable sites. These areas offer land at grid scale, but they also demand long transmission lines and hardened equipment. Small pilots were no longer enough. The plan now points to more than 225 renewable energy bases, with combined capacity around 455 gigawatts. The frame holds 225 bases and 455 gigawatts, then tightens to Kabuchi. From that national map, the lens settles on one desert in Inner Mongolia, among the plan's 225 bases. Kabuchi receives more than 3,000 hours of sunshine each year, so the choice begins with physics, not empty land. On the ground, the first frame looks hostile to equipment. Dry air, loose sand, and summer heat above 40 degrees Celsius. Sand hits glass, the grains scratch across panel surfaces, while hot module cells lose electrical output as temperature rises. Then the map changes. Solar radiation in Kabuchi reaches roughly 1,600 to 1,800 kilowatt hours per square meter each year, a high resource level by Chinese project standards. On an insolation map, the desert is not blank. It is a bright zone across the northern interior. The second frame pulls wider to area. Kabuchi covers about 18,600 square kilometers, with low population density and open tracks for arrays, roads, inverters, and maintenance corridors. That scale matters because utility solar needs spacing, access lanes, substations, and room for expansion. The third frame adds wind. Across many northern Chinese deserts, average wind speeds reach 6 to 8 meters per second, enough for utility wind turbines when terrain and grid access allow. Metal frames tremble. Solar output peaks during daylight, while wind often contributes after sunset, so hybrid bases can smooth power delivery before electricity moves east through long transmission lines. The threat remains physical. Sand fouls glass, moving dunes complicate foundations, and wind loads test the mounting steel. After sun, wind, and land are measured, crews move to site surveys, row marking, and preparation of the sandy foundation under the frames. With Kabuki selected, the job shifts from maps to exact measurement, insulation, wind, ground strength, and grid access. How does a scattered set of readings become a buildable field? Through a digital model. For several months, survey teams combined satellite data, drone passes, and solar radiation monitoring stations. Each source checks a different risk: sunlight intensity, wind direction, soil stability, and distance to existing transmission lines. No steel yet. The layout is still data. Energy modeling software then converts those inputs into row spacing and array tilt. Engineers also test mutual shading because tight rows can cut output during morning and evening sun. A few degrees matter. Too little spacing saves land but loses generation. By the time machines reach the sand, the construction phase already has its geometry. The approved layout moves into fieldwork, where survey marks must become a real graded site. Once the survey marks move from the model onto the ground, the digital grid meets terrain that only looks simple from afar. The software has fixed row spacing and tilt angles, yet the site contains shifting dunes, loose soil layers, and weak sand that can distort a clean line before construction starts. Flat in the distance, unstable under load. The first task is not installing panels, it is turning moving terrain into a controlled work surface. Bulldozers and excavators clear shrubs, large stones, and natural obstacles that would interrupt future rows. Then grading machines cut uneven dunes and push sand into low areas, creating a smoother plane for thousands of steel supports. The same leveling preserves the geometry of row corridors and service lanes, so maintenance routes stay inside the design instead of drifting with the ground. That is the hidden risk. If natural waves remain, thousands of support points lose alignment, and panel tables can twist before the array is assembled. After leveling, the basic surface exists, but the bearing work still belongs to underground metal. The graded surface fixes position, not strength. Wind loads up to 140 kilometers per hour, sandstorms, and day-night thermal movement must pass into steel below the loose layer. That changes the job. The solar field needs anchors, not a slab. A hydraulic pile driver stops over a marked coordinate. Its mast aligns with the survey point, then the ram presses a galvanized steel pile into the sand. Dull hydraulics hit in a steady rhythm. Metal vibrates and dry grains collapse around the upright as it moves 1.5 to 3 meters down, through the weak upper layer and into firmer ground beneath. Each machine can set about 300 to 400 piles per day. One machine, one day. Across a 1 gigawatt plant, foundation piles alone can exceed 200,000 units. The spacing between them usually stays near 3 to 6 meters, because the upper tables must land on repeatable bearing points. If that grid drifts, the future tracker rows inherit the error. Galvanized coating matters here. Zinc protects steel from corrosion, while abrasive desert dust keeps scratching exposed surfaces. The pile method also cuts the amount of concrete placed on site, which reduces curing work, water demand, and heavy delivery traffic across prepared sand. From above, the result is not a visible foundation, it is a hidden grid. For a great solar wall scale project, the count moves from hundreds of thousands to several million steel piles, with upper metal still waiting above every anchor. Once the buried anchors set the grid, crews build the upper mechanics. Long beams, galvanized steel, high-strength aluminum, and trackers that hold the working angle through the day. The first beam drops onto a pile head, aligns with the row, and locks under a fastening plate. Metal clicks in morning light. The sound is small, yet this joint belongs to a frame designed for 25 to 30 years, from -20 to more than 40 degrees Celsius. The materials carry the risk. Galvanized steel adds zinc coating, which corrodes before the structural steel and delays failure in dusty air. High-strength aluminum alloys reduce weight on the piles, but clamps and contact points still need protection. Desert service life depends on heat, corrosion, and steady sand abrasion across exposed edges. Beam after beam, the sections form rows stretching for kilometers across anchored piles. Below, steel fixes position. Above, geometry becomes generation. Many modern fields add movement to this metal. A single-axis tracker rotates the row around a longitudinal tube, using drives and linked supports. At sunrise, the table tilts east. By afternoon, it is turned west to improve the incidence angle. The gain is large. Against fixed racks, tracking can increase electricity generation by 15 to 25%. For a 10 gigawatt project, that boost equals 1 to 2 gigawatts of added capacity without another station. The rows start following the sun, while crews move to module mounting, the grounding circuit, and operation in sand. After crews align steel rows across the desert, they load them with 400 to 600 watt panels, one module at a time. The weak point is not the glass, it is the fastening. Aluminum clamps grip the module frame, and specialized bolts lock it to the rail. No loose edge. Modern modules usually use tempered glass and aluminum frames because desert sites bring abrasive dust and wide day-night temperature swings. That choice limits flexing, edge damage, and surface wear, but installation still decides reliability. Each panel must sit square, tight, and electrically safe. For a station near 1 gigawatt, the panel count can exceed 3 million units. Each module produces only 400 to 600 watts. Small output, massive repetition. Rows stretch for hundreds of meters, and every repeated joint carries wind load, sand impact, and vibration for decades. In the Great Solar Wall, the count moves into tens of millions of modules, so speed cannot replace torque control. Crews repeat the same sequence. Place the module, seat the clamp, tighten the bolt, check alignment. Metal clicks. A crew tightens the last clamp in one long row, then moves to cable connection. With more than 3 million modules secured, the next task shifts from clamps to electrical collection. Each panel produces direct current, while the grid needs alternating current, not usable yet. Crews link dozens of modules into one string, then group many strings into large arrays feeding inverter stations. Cable trays carry the output in controlled circuits because a loose connection can drop a full string. At the inverter station, the tone changes, a low electronic hum, switching clicks, then fan noise. The inverters convert DC into AC matched to China's national grid, which operates at 50 Hz. This step is not optional because the grid accepts power only when voltage, frequency, and phase stay synchronized. Protection equipment watches for faults before export. From there, substation transformers raise voltage to hundreds of kilovolts. Higher voltage lowers current for the same power, reducing heat losses in long conductors. Relay protection and synchronization equipment check the outgoing line before it joins the corridor across several provinces. China's ultra-high voltage lines carry desert power at up to 1,100 kilovolts over more than 3,000 kilometers. Once power leaves the inverter yard and enters the transmission corridor, the weak point moves back to the glass. A layer of desert dust, thin enough to look like a film, blocks incoming light before it reaches the cells. Output can drop by 20 to 30%, not a wiring fault, a surface fault. The contrast is sharp. The plant sends power through high voltage equipment, yet loses yield to sand on glass. Cleaning cannot rely on water because the site sits in a dry desert zone and covers tens of square kilometers. So fleets of robots move along the panel rows on rails or guided wheels. Central control assigns routes, while sensors and navigation algorithms keep each unit away from obstacles. The first frame is dull glass with a beige line of dust across the module. The next pass is mechanical. Soft polymer brushes sweep the pane, air jets pulse, and a low dry rasp follows the robot along the row. A small cloud of sand slides off the edge. Those brushes matter because photovoltaic glass often carries an anti-reflective coating that can be scratched by harder contact. One machine can clean thousands of square meters within a few hours. The fleet usually runs at night or early morning when modules are cooler and cleaning does not shade peak generation. When battery level falls, the robot returns to a charging point fed by the solar farm itself. It uploads status in real time. Route done, fault detected, charge needed. This is the maintenance layer behind the Great Solar Wall. Automation and artificial intelligence reduce the need for large crews, but they do not remove the schedule. Over 25 to 30 years of operation, high output depends on repeated dry cleaning of the panel surface. With dry cleaning now handled by robots, the next operating constraint sits below the modules. Engineers raise the panels 2 to 3 meters above ground, and that clearance changes the land plan. Why lift them that high? To keep shaded strips where grass can survive and sheep can graze. The format belongs to agrivoltaics, and operators often call it solar grazing. In parts of the Kabuki Desert and Inner Mongolia, they use that logic inside solar farms. The shade reduces soil heating and slows moisture loss, so grass appears in protected zones between the supports. Not bare sand, usable ground. The engineering gain is maintenance. Controlled grazing can replace mechanical mowing between rows, cutting fuel use, machine passes, and crew time. Short vegetation also removes dry material that can carry flames under cables and inverters. Fire risk drops because feed becomes fire control. The scene is quiet but technical. Hooves tap dry soil. Wind moves the grass under the glass with no mower crossing the frame and no heavy equipment idling
idling nearby. From above, flocks move through long corridors while millions of panels extend over them. Every gap between posts gains a job. The project no longer ends at exporting electricity or keeping glass clean. In its final operating layer, land inside the plant still produces value. Sheep move beneath the rows, and the station keeps sending current with no people visible.